Hello everyone, today I would like to introduce you the paper we submitted for this SCV, and the title is Masked Autoencoders are Efficient Class Incremental Learners. This work was completed by Nankai Universities of Florence and Tencent Into Lab. In this paper, we will explore the research on the masked autoencoders in the field of incremental learning. Before introducing it, let us first review the masked autoencoders. MAE are scalable, self-supervised learning methods suitable for computer visions, and its approach is simple. We mask random areas of the input image and then reconstruct the missing pixels. The approach is based on two core designs. First, MAE designs an asymmetric encoder-decoder architectures where the encoder operates only on visible image regions and is equipped with a lightweight decoder to reconstruct the original image from the latent representations. Second, in this work, finds that masking the input image with a high proportion, such as 75%, can yield a non-trivial and meaningful self-supervised task. So in this paradigm, the model's task is to reconstruct the original image by masking the regions. Compared with the traditional classification labels, the reconstruction task requires the model to predict richer information, including details and structures of the image. Through occlusion modeling, the model is forced to understand the connections and the interactions of different areas in the image so that it can accurately restore the content of the occluded area. Next, let's look at the background of our research problems. Incremental learning is a very important concept in the field of machine learning. The goal of incremental learning is to learn new tasks without forgetting previously learned knowledge. So why do we need incremental learning? In machine learning, we often need to constantly adapt to new tasks and data. However, traditional learning methods may forget previously learned content when learning new tasks, which is called catastrophic forgetting. To solve this problem, we need a way to maintain previously learned knowledge while being able to learn new tasks efficiently. One way to address catastrophic forgetting is to use richer and higher quality replay data. In this scheme, we can see the schematic diagram below, which shows the process of replay data generation using a generative adversarial network. MAE naturally has the abilities to expand more replay data because we can mask the replay images and return only a small part, and then MAE can reconstruct similar complete images for replay training. However, we find that using MAE directly will cause the reconstructed images to be blurry and rough, which may increase the model's forgettings of old task knowledge. So considering these factors, we propose the model structures of the two-way MAE in the figure. It can be seen that after the input image is masked, it will be calculated by the main branch and the detail branch respectively, and will be supervised at the feature level and image levels. At the feature levels, the features of the two branches are fused and used as the output of classification information, and the images reconstructed by the two branches are added together as the output of the final reconstructed image. In addition, we also add detailed laws to the data branch to allow the model to learn how to reconstruct the detailed information in the image. Regarding to the loss functions, first, the classification loss is optimized by fusing the features of two branches and use cross-interface loss. In terms of reconstructed loss, we follow the MER articles and use the mean square errors for training, and this not only allows models to restore the data of the original image, but this self-supervised training process also allows the model to learn more transferable representations, allowing the model to better adapt to previous knowledge between different types of incremental tasks. Finally, in order to make up for the lack of details in the reconstructed data in the original image reconstruction paradigm, we additionally use detail loss to make the pictures reconstructed by the model closer to the data of the old task, thereby better alleviating the forgetting problem. We conducted experiments on several classic image classification datasets, such as Cipher 100, ImageNet subset, and ImageNet to evaluate the prediction accuracy and forgettings of the model. The accuracy is measured by predicting the top one classification accuracy, and the forgetting is measured by calculating the degree of declinations in accuracy of each classification task when the model is trained to a later stage relative to the previous stage. The lower the forgetting rate, the more suitable the method is for incremental tasks. Through the above targeted model designs, our method achieves better performance than previous models in the incremental tasks. In ablation experiments, it was shown that the use of a dual branch MA structure is very effective in improving the performance of the model and coping with the challenge in incremental learnings. Furthermore, with the help of these models, we successfully improved the qualities and quantities of replay data, thereby enhancing the model's abilities to reduce forgetting. We also tried different mask ratio and found that masking 75% of the images worked best. Considering that an important factor in our approach is the richer replay data, we also compare different amounts of replay data and different methods of generating this replay data. The table on the upper right reflects the help of our method in class incremental learning at a self-supervised level compared to vision transformers. And the table below illustrates that replay data recovered through MAE is more suitable for class incremental learning to consolidate old knowledge. In these tables, the top to bottom method use generative adversarial networks, learnable parameters, spatial downsampling image, JPEG compressions, and the foreground separation to improve the replay data. And our method outperforms optimally in this aspect. Regarding the pictures recovered by the dual channel MAE structures, we can see that the model has the abilities to reconstruct some pictures in the first few tasks. We believe that this is actually due to the fact that the self-supervised task of image reconstruction is less efficient than incremental tasks. The correlation is lower for classification tasks because the data distribution of images in RGB space is actually more stable and uniform than in semantic labels. In addition, the image reconstructed by the data branch also learns some details in the image. To summarize, we delved into the effectiveness of masked autoencoders in incremental learnings, and our method is significant for solving the catastrophic forgetting problems, retaining past knowledge, and adapt to new tasks. Through a series of experiments, we verified the superiorities of our method, and compared with other methods, our dual branch MAE method shows better performance on different datasets. This further confirms the effectiveness of our approach in dealing with the catastrophic forgetting problems. In future research, we will continue to improve and expand our method, explore more application scenarios, and further improve the performance and efficiencies. We will continue to promote the development of the fields of incremental learnings and provide more powerful tools and methods for solving practical problems. So thank you so much for your listenings, and our code implementation will be released in the link below. You are also welcome to continue this research and carry out new work.